Hello everyone, this is Bindu Kumar here. In this live stream, we are going to look at what are containers. So I'll be giving a beginner's introduction to what are software containers, why they are so popular. The complete explanation will be from the perspective of a beginner, someone who doesn't know what are containers. So of course, we are not going to get into the details of it, right? So this live stream will be perfect for someone who's new to the concept of containers. As with all my videos, in this live stream as well, we are going to start with the problem statement. Every software, every design pattern ever designed was always created to solve a problem. The same applies for containers as well. The containers were created to solve a particular problem. So let's first start with the problem statement. Then it becomes easy to see why the containers were created and how they work and how they are useful. First, let's look at a typical software system setup, meaning what is it that you need for a software to run? So the first obvious thing we need is hardware. So hardware consists of your CPU, the motherboard, memory, storage, and network drivers, all of it, right? So you pretty much know what hardware is. Then comes the BIOS. So we don't, most of us, don't use or are even aware of what BIOS is, but it's very much there. The operating system that we use, like Windows or Linux, cannot directly interact with the hardware. There is one more smaller operating system before it, smaller, or let's call it the core operating system. So that is called the basic input output system, or for short, BIOS. So this is what interacts with the hardware. You may briefly see it when your computer is booting up and you see some command line text in black and white text. So that is your BIOS. Next is obviously the operating system, right? So the operating system can be either Windows, it can be Linux, it can be Mac, right? There could be other operating systems as well. On top of this, we will usually have an application software. So what are some examples of application software? We have .NET Core, Oracle Database, Java Virtual Machine, Python compiler. So these are all examples of an application software, meaning they are the platform or the framework on which softwares can run. On top of this, we have the custom application that we create, such as a website, a simple script file, a Java program, or maybe some kind of a reporting tool, right? So the custom application is our end product. But you see, to be able to run just a website or a script file or a Java program, we need all of these, starting from the hardware, the BIOS, the operating system, and the application software. So you can see how complex it is to build and to set up and maintain such a complex layers of system in order to support your application, right? So the same applies for all of us. So we may be working for some software firm, we may be building our software, right? But without these underlying layers, our software will not run. So these are the prerequisites, or this is the backbone of a software. We need hardware, BIOS, operating system, and application software, right? So this is what is required to run any software. So next we'll run into the problem statement of these systems, right? So after some time, your software may be running slow. maybe because it needs more resources. The very first thing that we do is something called as vertical scaling of the system. So what is vertical scaling? Vertical scaling is where we increase the resources available on the computer, right, based on its limitations. For example, let's look at this typical setup. We have the hardware, BIOS, operating system, and application software, on which we have the custom application. So if we experience that the application that we are running is slow, there are few things that we can do, such as increasing the count of processors. Now, this is something we may not do it on our laptop, but in data centers and enterprise grade servers, this is definitely an option where you can add more processors, hence increasing the compute and computing capability of your computer or of the server, let's say. On the same lines, we can increase the amount of memory or RAM that's available. Usually it starts with 8, but you can scale up to, let's say, 8, 16, 32, 64. Then of course there are servers that support much more than that. And then finally you have the storage. So the computer will always support increasing the storage. But then every motherboard has a limit as well. You really cannot exceed more than a fixed number of processors. So here you can see the limit is only 4 processors. If my software performance does not get better even after 4 processors, I really cannot include more processors. Simply there is no provision, right? The same applies for memory and storage. The motherboard, every motherboard will have some kind of a limit, an upper limit up to which you can extend. After that, there's nothing that you can do, right? So these are challenges of vertical scaling. Every motherboard has limits, and of course the operating system as well. So let's suppose you're using Windows 32. If you're using Windows 32-bit, it can only use up to I believe 4 GB of memory. Anything more than that, it simply will not support, it will not detect, right? So if you have to use more than 4 GB, then you'll have to install the Windows 64-bit, right? So there's some limitation on the operating system. Applications also may have limited CPU license. So in the previous slide, I mentioned Oracle is a database. Oracle is a licensed software, and that license will say you can only run it on one processor, right? So what do you do now? Even after you increased the processor count by 4, it still won't help with the performance because the Oracle application will only use one processor. Also, the last point is scale up requirements may be temporary, meaning today I may have a requirement that I may, there are more users logging into the server to use my application. But a month from now, there may not be that huge requirement. One example is take Amazon or any retail chain. From time to time, they have these, big sale festival when they shell out a lot of discounts, and they see sometimes exponential increase in the number of users who are accessing it. So just to give a one scenario, on an average day, let's suppose my company gets around 1 million online users, right, logging in. Now if I shell out a discount, if I do a promotion, then in that particular week I can expect up to 20 million users to visit. So how do I handle that? Right. So one way is to do this vertical scaling of my systems. But then as you see, it's temporary, meaning what do I do after that 1 week? I have already invested in these processors, this memory and storage. All of that will be again underutilized. Right. So which means I'm not getting the return on the investment that I did. Okay. So this was about vertical scaling. Now, the next step is to do a horizontal scaling. Horizontal scaling means we create copies of the machine. Okay, so here you can see this is taking the scalability of the system to the next level, where we know that we have exceeded or we have met the limitations of the server. So the next best thing I can do is create another server, right? So here you can see I started with one system, but now I have 4 systems, and in each system I have installed all of this hardware, BIOS, operating system, application, and custom application, right? Here the same problems appear, which is every system will hit a limit, but then there are some new challenges, right? So the first challenge is distributed applications are complex to maintain. So if I have 4 servers, and let's suppose I am deploying my Oracle database. My Oracle database is running on all these 4 servers, right? And although they are running on different servers, they have to act and behave as a single application. If I write to Oracle database, I don't have to worry about which system I'm writing to. I should always write to one database, and it will replicate all the records across all the servers. So this is a distributed software. Now distributed softwares by nature are very complex to maintain. They require a lot of maintenance, lot of monitoring 24/7, right? So by nature the distributed applications are complex to maintain. Then of course you have increased hardware maintenance, right? Of course this is obvious because we added new servers. There is a lot of maintenance that needs to be done on all these hardware in terms of their power requirements, in terms of any failures in the components and so on. The same challenge as before. Scale up requirements may be temporary. Buying a hardware is a significant investment, especially for an organization. And once you buy it, you want to make sure that you have some kind of returns on that investment. Now, the previous example that I gave, where a retail chain has a sudden demand, right? But it is temporary. Now, of course, somebody can buy these many servers, and for that week or two, they will be able to support the large number of users. But what happens after that? Once the number of users come down, you really don't need to run these 3 machines. But until then, what do you do with them? How do you utilize them? Right? And the problem with servers is it is not very easy to reassign them for different tasks. I can give you an example. Suppose we have installed Linux on one machine, right? And let's suppose there is a website that's running on that Linux machine. For some reason, we don't need it. We don't need that. We don't need one server of that Linux. Now somebody will say, okay, I need to install Oracle database and I need a server. So we can reassign this, but it's not that easy. There is significant effort spent in formatting the server, installing Windows, right? Removing Linux, installing Windows, installing Oracle. All that could take, at least a couple of days worth of effort. So you see, reassigning these servers for different tasks is not an easy task. It's time consuming. It's very tedious. So these are some of the challenges with horizontal scaling as well. So the industry recognized these 2 challenges, and they came out with virtualization as a new concept. So what is virtualization? Let's look at it with a simple architecture diagram. So we have the hardware, we have the BIOS as usual. Then we do not install the operating system. Instead, there is something called as hardware virtualization. Okay, so hardware virtualization, you can think of it as also as software, but it's not exactly like Windows or Linux, right? So a few examples are Citrix Zen, Microsoft Hyper-V, and then you have the VMware's ESX. So these are all hardware virtualization. So what do? They let you run multiple operating systems on the same set of hardware. So here is an example. You can see We have the Ubuntu Linux operating system. We also have the CentOS Linux. We also have a Windows 2016. All of them coexisting on the same hardware or on the same server. All this is possible because of hardware virtualization. Now, using this new layer of hardware virtualization, it is possible to assign resources to each of these. So I can say Linux will get 4 GB, CentOS will get maybe 8 GB, and the Windows will get, let's say, 16 GB of memory, provided all of that is separately available. Right. On top of these operating systems, you can install whatever application is required. Okay. The other solution is called operating system virtualization. Right. So let's also look at this. Again, we have the hardware, we have the BIOS, we have the operating system installed. It could be either Windows, Linux, or Mac OS. And then instead of virtualization hardware, we have virtualization software. Examples are Oracle's VirtualBox, QEMU, or VMware Workstation. Now, what the software allows you to do is you can create a computer under a computer, right, or inside a computer. I know it's a little difficult to understand if you're new to it, but you may have heard of the term virtual machines, right? This is exactly that, meaning you have your, let's say, normal laptop, for example, Windows. Now I'll go and purchase a new laptop which comes with Windows. Now I need to learn Linux. So what do I do? Do I uninstall Windows and reinstall Linux? Of course I can do that, but it's going to cost me time. Of course I'm going to lose all my Windows software and any documents that I would have placed. So what do? I will install this virtualization software like VirtualBox or any of that. Once that software is installed within Windows, I can use that to create new machines which run under my operating system. Right. So using I use VirtualBox, for example, right? Using VirtualBox, it's perfectly possible to create Linux operating systems, Windows operating systems, Mac, and any other operating system that it can support. So now if I have to do some learning on the Linux, I just have to start that virtual machine. But again, there is always the operating system that is underlying here. Right? So these are the two solutions that have been created in the past decade to address these problems. But still, the problem of the different layers still exist. Meaning, just to run one application like REST API or a website, we need all these different layers, starting from hardware, BIOS, operating system. And even within this virtualization, you can see there is again an operating system. In fact, it is an added overhead, right? It's increased overhead. We again are installing the operating system. You have to go through all the steps of putting in the setup files, installing the operating system, and then installing the application and so on. So in fact, there are few things that are good with it, but there are a lot more shortcomings as well. So in this slide, we will look at some of the common challenges between both hardware and software virtualization. So as I said, the applications still require an operating system and an application framework. The operating systems, whether they are Windows or Linux, they need maintenance, they need updates, they need fixes, right? So there's a lot of maintenance to be done. And also the scalability is limited to the vertical scalability of the machine. Right? Still, all of these are operating under one server. Okay, and also it's difficult to manage applications distributed across multiple machines. So if I have a website that's running under two different virtual machines and two different servers, it's very hard to manage them. Right? The setup will be quite complex in order to manage it. Now we will look at the anatomy of an application, meaning let's take a deeper look into what is an application, what exactly does it require. So the first thing, as I said before, is the hardware. Now hardware is made up of multiple components: the motherboard, CPU, storage, network card, and memory. And of course, there could be many other components as well. Then we have the BIOS, which is the basic input output system. We have the operating system, such as Windows, Linux, or Mac OS, and then the application software. On top of which we have our custom application. But if you look deeply at the custom application, such as the website or the VB script or a Java program, what they really need, or the only dependency they have, is on the application software, right? They really don't interact directly with, let's say, the operating system or the BIOS or the hardware. Most of their interaction is with the application software, right? So now let's take that picture. Here we have removed the hardware, right? And what we have is just the operating system, application software, and custom application, right? And in the custom application, you can see that we may have different kind of programs. In the next slide, we will look at one operating system as an example. We will take Linux, right? So Linux is made up of its own components such as kernel, display drivers, peripheral drivers, and so on, right? Upon which we can have application softwares like Oracle database, Java virtual machine, and then we can have our custom applications. We are taking Linux because Linux is one, it's open source, right? It's totally free. Since it is open source, you have complete freedom to play around with the files, meaning let's suppose you want to remove some of these components, you can do that. And that's what we are going to look at the next slide, right? So the next slide does exactly that. We have removed all the unnecessary software from Linux, or all the unnecessary drivers from Linux. Why? Because we no longer have an hardware, right? We have just the Linux and the core of it, which is also called the kernel, right? The most basic engine or basic driver of Linux. Then we have, in this example, we just have the Java virtual machine that is required to execute any Java programs. And then we have the custom application that we developed, right? Which is a jar file. If you look at it, this is a very lightweight packaging of the software called container. So a container is a very lightweight packaging of the operating system, the application software, and our custom application. It is lightweight because we are assuming there is no dependency on the hardware, because we have completely removed the hardware from the architecture. And when we do that, the operating system can be made very light by removing much of those peripheral drivers. Now here, if you look at Linux, it is only used to execute or host the Java virtual machine. So it has no interaction with, let's say, a CPU, a keyboard, a mouse, a display. All of those drivers are taken out. And when you do, you end up with a Linux image that is very small, sometimes just 20 or 30 MBs, upon which you can install Java virtual machine and then a Java program. Now all of this taken together becomes a container. Now let's look at the next slide to see how this container works. So when it comes to a container, of course, we will have some hardware, but the hardware we are really not worried about, right? We always start with the operating system. Linux is an example, right? So Linux operating system, we have a container platform called Docker. I'm sure many of you must have heard of it. Docker is quite a popular, a very broadly used container platform. So Docker is what can host or run these containers. These containers are completely isolated from the operating system, not the operating system, but the underlying hardware. So as long as you have Docker installed on any machine, you can run this container there. Okay, so in the next slide, we're going to see how these containers can be created. They look a lot like virtual machines, don't they? Right. So in this slide, you can see there are three containers. All of these three containers may have different operating system, a different application software, and a different custom application. But they're all running on this container platform called Docker. They look a lot like virtual machine. However, they are very lightweight because they are not full-fledged operating systems. They only have the base kernel. Many times these containers are just like maybe 50 MB, 60 MB in size overall, including the application software and your custom application. But if you were to set up a virtual machine where you will install Linux or install Windows and do the usual thing that you do when you set up a new computer, the resulting file is usually at least 50-60 GB, at the minimum. Right? So just do a comparison. Where is 50-60 GB versus maybe 30-40 MB, right? So that's how lightweight a container can be. And the benefit is not just the size of the container, but also the boot time. With Windows or Linux, we usually have a boot time of a minute. Sometimes it can be seconds, but then we are not counting in the boot time of our application, right? Once Windows is started, we need to start our application framework, and then we will have to start our custom application, right? But with a container, all of that can be started within milliseconds. The reason is the operating system is lightweight. It does not have many of these peripheral drivers for input, output, storage, memory, CPU handling, and so on. So that makes it very quickly bootable, right? So that's one of the benefits. The second is millisecond scalability. Since the files are so small and also that it has lightning fast boot time, I can easily make copies of the container, right? So if I have a script that will be if I have a website that will be accessed by let's say thousands of users, I can quickly increase my number of containers. So right now you see it's only 3 in this particular slide. I can go from 3 to 300 within a minute, right? Which is simply not possible with the traditional scalability approach of either vertical scaling, horizontal scaling, or even virtualization, right? So that's one of the benefit. The other is minimal or no application downtime. So I can easily replace these containers with new containers, right? Without having to, let's say, shut down the server or reboot the server or any of those nuisance. So that was about the birth of a container. So the next is about the lightning fast scale up, scale down, which we'll look at in the next slide. So I said, when we have a virtual machine, scalability is a big problem. right? No matter which kind of scalability you take, vertical scaling, horizontal scaling, they all have their challenges. But with containers, you can achieve lightning fast scale up and down, and the reasons which I just explained. Um, it it is it is lightning fast in terms of boot time. Also, it's very lightweight in terms of file size, so you can very quickly make copies of it and you can boot all of them simultaneously. So you can go from 3 containers to 300 containers in just a matter of minutes. So that gives you the flexibility to handle large demand. So look at the example that we talked about before. If you are expecting more users to use your web application in a particular week, just before the week starts, you can run these containers, right? You can scale them with just one command. You can, instead of running 20 containers, you can run 2000 containers, right? So that's one obvious benefit of a container. Next, we have the portability, right, which is coming up in the next slide. So the advantage of having these containers is they can be run anywhere. They can be run in data centers as long as you have the same container platform. They can be run on some public cloud like Amazon AWS or Google. It can be run on virtual machines, or it can be run on a physical machine such as your laptop or your developer machine. So remember the common excuse of a software developer when something doesn't work. You say, uh, well, it used to work on my machine. I'm not sure why it's not working on production, right? That's a excuse that we are all used to, right? Listening from others as well as using that excuse ourselves. That's because many things can change between, let's say, my machine and the actual machine where it's going to run. Many things can change. It may be dependent on the operating system. It may be dependent on the CPU resources or the memory that's available. But that is no longer an excuse. With a container, you're packaging everything, right? From the operating system to the application software and the custom application. Right? So the advantages, now you can simply make a copy of that container and run it on any of these different environments: data center, cloud, virtual machine, or a physical machine. So what you develop on your laptop is exactly what you're going to run on the server. So the chances of the code changing or getting affected is very, very less or close to zero. So that was about the portability of containers. Now, talking about containers and the operating system, Linux is the preferred container operating system. And the reasons are pretty simple, right? First, Linux is open source, it's freely available, anybody can download it. You can not only download it, but you can customize it to a great deal, provided you know how to use the source code of it. And Docker was always built for Linux. Docker as a container platform, which is a software, was built for Linux. Now, the obvious choice to build my container operating system is also Linux. So as you can see here, I'm hovering the mouse over the container operating systems. You can see all these three are Linux in this example. The reason is this: I can make a copy of Linux. I can remove all the unnecessary packages and drivers that are there. I'll just keep the Linux core kernel. That way, I'll bring down the file size from several GBs to maybe few MBs. And then I'm free to distribute it as well, which means I can make multiple copies of the containers that I'm going to build. So, which is why Linux is the preferred container operating system. right? However, Windows is trying to catch up, but they are not there yet. Since Linux is open source, there are a lot of images that others have built that you can use. Here is a screenshot from Docker Hub. You can see I searched for MySQL. There are other people, just like yourself, who are very enthusiastic. They have already taken the effort to building an image. Now that one container image will have Linux installed on it, and they would have also installed MySQL database on it. All you have to do is make a copy of it and you can run it on your machine, right? How cool is that? There are literally thousands of containers that are container images that are available for you, and many software vendors are rolling out their software in Dockers because it's so easily portable, and you can easily install it and you can just try it out. So with that, I want to conclude that containers are for everyone. It is community driven, so there is a lot of support that you will find when building your own containers. So in a quick summary of everything that we discussed, we are coming close to the end of this live stream. I just wanted to summarize. So containers are a lightweight packaging of the operating system, the application framework, and application. This results in lightning fast boot time and also very small file size. The third point is they are immutable. Immutable means, let's suppose there is a change in one of the hardware, right, in a traditional setup. Now there will be a downtime, which means I have to intimate everyone that the application is not going to be available, right, until I fix the hardware issue. Or let's suppose I have to make a change to my custom application. On a weekend, I will say the application will not be available. We will send out emails, we will make the fix, and so on, right? But with containers, all of that nonsense are gone away, right? Because I can have my old containers running while I build my new containers, having the latest source code or the latest bug fix or whatever it may be, right? So I can quickly make copies of my new containers, and when my new container is available, with just few commands and within few seconds or minutes, I can destroy all the existing containers and spin new containers, right, without any downtime, without any change to the hardware. And of course, they can be scaled up and down on demand. And also about the portability, which is the same containers can be ported between different environments like servers, virtual machine, cloud, and data centers. And then Linux containers are totally open source and free. One drawback, or one limitation that the containers have right now is you can run Linux containers only on Linux platforms, right? So that's one limitation at the moment, but we'll have to wait and see if in the future they'll get rid of it. So if you have to run any containers that have Linux as the operating system, it can be run only on a server that also has Linux operating system. So the same applies for Windows as well. Windows only supports Windows containers. So Windows containers are available. However, they're not that frequently used. The reason is there is not much support for it from the community. Also, the resulting file sizes are quite huge. I think last time I checked, a very lightweight Windows container was still around a GB, or maybe several hundreds of MBs also, which still does not fit into or not as agile and uh, lightning fast as a Linux container. So Windows containers still have a lot of catching up to do. So that's all I had for this live stream. I hope those who are watching this live found it useful. We still have 4 minutes to go. Are there any questions? Any questions? Any feedback? How was the live stream? Did you find it useful? Was it easily explained? My main objective is not into get into the details, but to be able to easily explain a concept. I know many in the industry who have years of experience in other technology like a database or some reporting tool and so on, but the containers are something that are catching up fast, and you really need to have some basic knowledge of it. Now, when I tried myself, I had a hard time trying to understand because all of the resources that I found neglected to explain this concept from the ground up, and which is what I try to do with this live stream. We have 3 more minutes to go. Any questions so far? All right. So if there are no more questions, then I'll be ending this live stream. Thank you so much for joining this stream. I hope you found it useful. Please remember to like and subscribe if you found this video useful. Also, I would appreciate if you would give your feedback in the comments because I'm planning to make these streams much more regular. I'll be bringing in a lot of content. So I'm really looking for all of your feedback. Thank you so much. You have a great day ahead.